Welcome to the CO2. We are going to discuss about Fourier series and frequency domain representation. The learning outcomes of this session are: you will be able to understand the concept of orthogonality, and you will be able to explore Fourier series. Now we are going to discuss the analogy between signals and vectors. So if you are going to consider two vectors v1 and v2 with an angle of theta between them, we can write the dot product between the two vectors v1 v2 as v1 v2 cos theta. Now we are going to discuss what is the component of the vector v1 along the direction of the vector v2. Now let us look at this diagram. Here the vector v1 is given by the vector OA and the vector v2 is given by the vector OB. We are going to draw a perpendicular from the point A to OB, which is intersecting at the point P. Now the component is this vector OP, which we are writing as C into V2. Now if we look at this triangle, we can apply the vector addition as V1 should be equal to C V2 plus the error vector VE. So we are writing V1 is equal to C V2 plus the error vector VE. Now here the constant C is called the component of the vector V1 along V2. Now we know that we can write the cos theta as adjacent side by the hypotenuse. So if you go back to the previous slide, we can see the adjacent side is CV2 and the hypotenuse is V1. Hence we can simplify as CV2 is equal to V1 cos theta, which we can write it as V1 V2 by mod V2. Now from this we are going to get the component C as V1 dot V2 divided by mod V2 whole square. Now this is the component of the vector V1 along the direction of the vector V2. So C is equal to V1 dot V2 divided by V2 modulus square. Now we can note that if the two vectors V1 V2 are perpendicular to each other, then the theta is 0, the cos theta will be 0, and hence we will get V1 dot V2 is equal to 0. Therefore the component will be 0. Hence if the two vectors are perpendicular or orthogonal to each other, then the component will be 0. Now similarly we are going to discuss what is the component of the vector x1 along the direction of the second vector x2. Now we can write that the vector x1 is equal to the component C into the second vector x2 plus the difference vector xt. Now this difference vector we can then write as x1 of t minus c into x2 of t. Now we are going to obtain the value of the component that will minimize the difference signal, which is xd. So in order to do this minimization, we are going to use mean square value of the difference signal, that is integral 0 to t xd whole square dt. In order to find whatever is the minimum value, we have to do the derivative d by dc of that integral 0 to t xd whole square dt and set it to 0. Now what is the value of xd? It is x1 minus c x2, and we are having the square here. Therefore you will get a minus b whole square, which is a square, which will be x1 square, plus b square, which is this c x2 whole square, minus 2ab, which is minus 2c x1 x2. Now this entire derivative must be equal to 0. Now when we are taking the derivative, you have to remember the derivative is with respect to the c. So the derivative of the first term will be 0 because there is no c here. In the second term we have c square. The derivative of c square will be 2c. And in the third term there is 2c. The derivative of 2c will be the constant 2. Hence, we can simplify this derivative as the integral 2c x2 whole square minus 2x1 x2, that integral dt equal to 0. From here we can write the component as c equal to integral x1 x2 dt divided by the integral of x2 whole square dt. Now we are going to discuss what is the condition for orthogonality of the two signals. Now the two signals are orthogonal, it means the component will be null. So when the two signals are orthogonal, the component C will be null or 0. So if you put the condition C equal to 0, then the condition for the orthogonality of the two signals is simply the integral 0 to t x1t x2t dt is equal to 0. Now here we are going to discuss another concept that is called orthogonal signal space. Now we are considering a set of n signals which are called basis functions b1t, b2t, b3t, so on till bnt, and they are having the energies over the time period 0 to t as E1, E2, so on till En. Now the energy of a particular signal we can write as Ei is integral 0 to t bit whole square dt. Now these set of signals B1, B2, B3 so on till Bn, they are called orthogonal signal space if all the signals in the set are mutually orthogonal to each other, which means that the integral 0 to t bi of t bj of t dt is equal to 0 if I is not equal to 0, and the integral bi of t bj of t dt will be ei if e is equal to, if I equal to j. Now here we are going to see the calculation of the signal components for the orthogonal signal space. Now we can write whatever is the signal x of t as a summation of that basis functions, summation I equal to 1 to n ci of t into bi of t. Here ci is called the component. So again we are setting the error function as the difference between the x and whatever is this component summation which is multiplied with the basis function. Now we can write this component ci as integral 0 to t x of t bi of t dt divided by the integral 0 to t bi of t whole square dt. This we can simplify as the component ci will be equal to the integral of x of t multiplied by bi of t dt divided by ei of t. Now we are going to discuss certain properties of the sine and cosine functions. The integral of the cos signal cos n omega naught t over one complete time period which is 0 to t naught will be 0. So we are going to tell that the integral 0 to t naught, where t naught is the time period, the integral 0 to t naught cos n omega naught t dt will be equal to 0. So if we are integrating the cosine function cos n omega naught t over a complete time period, that integral will evaluate to 0. Now this is second property. If we integrate the sine function sine n omega naught t over one complete time period 0 to t naught, that integral will be 0. That is integral 0 to t naught sine n omega naught t dt will be 0. These integrals are very easy to be proven to be equal to 0. Now based on this we are going to get the important orthogonality pairs. If we take the signal sine n omega naught t and the another signal sine m omega naught t, both of them are going to be orthogonal as long as n is not equal to m as per the property 4. that is the integral 0 to t naught sine n omega naught t sine m omega naught t dt will be 0 if m is not equal to n. Hence, the two signals sine n omega naught t and sine m omega naught t are orthogonal to each other. Now, similarly, if we take two cosine signals, cos n omega naught t and cos m omega naught t, those two signals will be orthogonal as long as m is not equal to n. Now, finally, the other pair of orthogonal signals is sine n omega naught t and cos m omega naught t. Now we are going to discuss some more properties here. So if you multiply a even signal with a even signal, the resultant signal will be even. And the next property says that when we multiply an odd signal with an even signal, the result will be odd signal. And the next property tells that when we multiply an odd signal with another odd signal, the resultant signal will be even signal. Now, the next property tells that when we integrate a odd signal over the complete time period 0 to t naught, that integral of the odd signal will be 0. The next property tells that when we integrate a even signal over one complete time period 0 to t naught, it is equal to twice the integral of that even signal over half of the time period, that is 0 to t naught by 2. Now we are going to discuss an important concept called exponential Fourier series. Let us consider a periodic signal x of t whose time period is t naught such that x of t plus capital T naught is equal to x of t. Now this signal will keep on repeating itself for every t naught seconds. Now the fundamental frequency is denoted by f naught, which is f naught is 1 by t naught. Now, using this exponential Fourier series, we can represent this periodic signal as a linear combination of the e power function e power j n omega naught t. Now, the exponential Fourier series equation we can write as x of t is equal to summation n equal to minus infinity to infinity c of n into e power j n omega naught t d. Now this is called the synthesis equation. So we are able to write the periodic signal x of t as the summation n is going from minus infinity to plus infinity cn into e power j n omega naught t. Now here cn is called Fourier series coefficient. Now the exponential Fourier series coefficient is given by this simple integral. C of n is 1 by t naught integral 0 to t naught x of t into e power minus j n omega naught t dt. This is called the analysis equation. Now here we describe a simple procedure to determine the Fourier series. The first step is we identify the time period of the particular periodic signal. Then we calculate omega naught using omega naught is equal to 2 pi by t naught. Then we compute the Fourier series coefficient Cn using the analysis equation, which is this equation 2. Then we are going to substitute the Cn values to get the signal x of t using the synthesis equation, which is the equation 1. Now here we are going to see a simple example how to compute the exponential Fourier series for a sawtooth signal which is having this particular waveform. Now from the figure we can observe that one time period of the signal x of t can be represented as here at the origin x of t is equal to t for the value of time from -1 to +1. So the time period t naught is 2. Hence we can write omega naught is 2 pi by t naught, which will be pi. Then using t naught is equal to 2 and omega naught is equal to pi, we calculate the Fourier coefficient over the time period -1 to 1. substituting the signal s of t is equal to t in the analysis equation 2 as Cn is 1 by t naught, the integral 0 to t naught x of t into e power minus j n omega naught t dt. Now t naught is equal to 2, so 1 by t naught becomes 1 by 2. The limits of the integral are over one time period. The one time period we are taking is from minus 1 to 1. So the integral goes from minus 1 to 1. What is the signal x of t? It is simply t. So we write t. Then in the place of e power minus j n omega naught, we know omega naught is pi. So we get e power minus j n pi t dt. Now we are going to do the integration and we are going to simplify this further using integration by parts, and we can finally write the value of the coefficient Cn as j by n pi into cos n pi minus sin n pi by n pi. Now we are going to substitute this value of the Fourier series coefficient Cn into the Fourier expansion or the synthesis equation while using omega naught is pi. So we can write the signal s of t as summation n equal to minus infinity to infinity Cn into e power j n omega naught t. So here we will substitute omega naught as pi and the Cn value is already calculated. So hence we get the Fourier series expansion or the synthesis equation as s of t is equal to summation n minus infinity to infinity j by n pi cos n pi minus sin n pi divided by n pi into e power j n pi t. This is the Fourier series. So the main concept of the Fourier series is we are now representing that sawtooth waveform by a combination of the exponential signals that are weighted by the Fourier series coefficients. I want to thank all the students for your patient hearing. Thank you.